Hello pre-calculus, I've got a new video for you. It's lesson 6. It's the second one on graphing rational functions. Now if you recall, we had asymptotes, horizontal and vertical. What I'm going to show you are the special cases to that where it seems as if we are for sure going to have an asymptote, but we end up not. So let's get started. So on my first one, f of x equals x squared minus 7x minus 8 over x plus 1. Now, if I were to try to just plot points, okay? So I guess instead of investigating it organically, I'm just telling you that there's not going to be an asymptote in the place where it should be. Let's investigate by just plugging everything into this calculator. Okay, so the top part of the fraction should be x squared minus 7x minus 8. All of that divided by x plus 1. So if we plot our points, let's get back to a regular setting. Let's start at 2 or 1 and go by ones. All right, so 1, negative 7. That's a point to plot. 2, negative 6. 3, negative 5. 4, negative 4. 5, negative 3. That's interesting. Okay. It basically is a line. Well, you know what? I don't trust this, so I'm going to look at the points in between. I'm going to make my table step a quarter, so 0.25. And at 1.25, well, let's go by halves. So 1.5 is negative 6.5, which is right here. 2.5 is negative 5.5. 3.5 is negative 4.5. Oh, wow. They're all still right on line. So what's going on left of that? Well, at 0, it's negative 8. At negative 1, it's error. Okay. And then at negative 2, it picks back up on the linear value. Down 1, left 1. Down 1, left 1. Down 1, left, error, but then it kind of picks up again. So it's kind of like everything up until this point works. But it's not an asymptote. It doesn't have behavior that basically hugs the dashed line. It basically says, hey, you don't exist right there, but everybody else is good. Now the question is, how do we determine this without just doing random point plotting? I want to make sure we've got the algebra behind us and not just use some random calculator that you found on the street. Well, I don't know if you guys noticed this, but the numerator is a factorable trinomial. 1 times negative 8 gives me negative 8, and those add up to negative 7. So my two factors are negative 8 and positive 1. And you can use that factoring shortcut when it's a 1 in front of the x squared. Oh, if I can cancel out a factor from both the top and the bottom, it creates a hole in the graph. Let's call it divide out. The factor is x plus 1 on top. Not only is there a hole in the graph, but it seems like the remaining part of the function x minus 8, that's exactly how the function manifests itself. It's exactly what the function becomes when you plot random points. How do you graph y equals x minus 8? You start at negative 8 on the y-axis. Done. And then it has a slope of 1 over 1. Up 1, right 1, up 1, right 1. This is big. All right? This means that I don't even need a calculator to plot these points. I can just, if it cancels out and reduces to a linear function, I can graph it as if it's a regular line. Except the point -1, -9 is a hole in the graph. All right, so now let's start with a fresh example. We've been talking about this one for nearly 6 minutes. Fresh example. So now we are very, very, very analytical with all this. We're saying, hey, if it's factorable, I'm doing it, top and bottom. Oh no, I don't like the looks of this marker. Arrivederci. Nice. Okay, where is it? The numerator is certainly factorable. 1, 2, 3, 4 terms, I can factor the first 2 by grouping and the last 2 by grouping. So you can divide out an x squared, which gives you x squared times x minus 3. We need to make this look like x minus 3, so you got to take out a -1. That gives you x minus 3 times x squared minus 1. Difference of perfect squares. So this is x minus 1 times x plus 1. And that's your numerator. So f of x equals, in its numerator, here, kind of, blah. That's the factor by grouping of just the numerator. The denominator looks like it's quick, it's an easier move. Negative for both of them because it's a minus plus action. 3 times 1 is 3 but adds up to 4. So it's going to be x minus 3 times x minus 1 to factor the bottom. Okay, so because of that action, there is a hole at x equals 3. All right, it's kind of like you have an asymptote at 3. It's like the opposite of the sign inside there. You also have a hole at x equals 1. Now you can determine the y values of those holes by plugging 3 in for x right here. So it's going to be 3 plus 1. It's going to be 4. So 3, 4. Can you guys see? You can see at 1, 2, 3, 1, 2, 3, 4. So there's an open circle there, and then a hole at 1, 2. Now our job is to graph the linear function y equals x plus 1. We just don't fill in those holes. Graph f of x equals x plus 1. So you start at 1 on the y-axis. It has a slope of 1, which means you can go up 1, right 1, up 1, right 1, up 1, right 1, or down 1, left 1, down 1, left 1, down 1, left 1. And then draw a line. We're just making sure that we leave the holes open. Stop. Stop. All right, so check it out. There were no vertical asymptotes. There were no horizontal asymptotes. I mean, I guess we found a 0, but don't worry about writing it in this case. I think in this case, these are the most important pieces of information that you guys need to take away from it. All right, what else do I got for you? Looks like there's going to be another factor by grouping up top. I guess I was just really feeling the factoring frenzy with this, you know. Take out an x squared. Oh, are we going to have difference of square again? That'd be too obvious, right? Anyway, x squared comes out, x minus 4. Divide out, I need an x minus 4, take out a negative 4. Oh, I made it too obvious. Two difference of squares back to back. So you got x squared minus 4 times x minus 4. This factors down to x minus 2 times x plus 2. Still got the x minus 4 going. And then over here, we just reincorporate the x minus 4 that's on the bottom part of this fraction. Lo and behold, if x minus 4 cancels or divides out, then there is a hole at x equals 4. How do we determine what the y value is for that hole? 4 minus 2, which is 2, times 4 plus 2, 6. 2 times 6 should be at 412. So unfortunately, I gave you a graph that only goes up to 7. Let's make every block 2. So you're going to graph. You know what? I think it's easier to graph this version of the polynomial than it is to graph this version, okay? X minus 2 times x plus 2 is what you're graphing. But we just talked about how to graph parabolas, so it makes way more sense to represent that equation with x squared minus 4. Because now you can say, it's just a regular old parabola. Shift it down 4 units. So 2, 4, and then it would be over 1, up 1. So it's like over half a block, up half a block. Same thing to the left. Then over 2, a full block, up 2 squared, 4. And then it's the same thing on this side. Over 3, it's going to be up. Wait, what did I say? Up 3 squared. Sorry about that. So 2, 4. You know what? Here. Plug into 3. 3 squared minus 4, 5. So you're going to be plugging 3, 2, 4, 5. Sorry, I had an Owsley moment just then. And then if you go all the way over to 4, 4 squared minus 4, 12. 2, 4, 6. 2, 4, 6, 8, 10, 12. That's not a point, though. It's a hole in the graph. It's okay on this side, not on that side. And all right, so I hope what this one taught you, oh, that's a really, it is what it is. It's a parabola. You know what? I'm not even going to fix it. They're not always linear when you divide out factors. Sometimes they're parabolas. Sometimes, let's check out number 4, something else altogether. All right, here's my last example. This video is pushing 15 minutes, so my apologies for the I don't know. I think we needed a 20-minute video. No apologies from me. All right, so right away you should be thinking, hey, the bottom looks like it's factorable using that same kind of factoring I just saw 2 times prior. Difference of perfect squares, one's going to be 4 minus x, the other's going to be 4 plus x. However, you might want to rethink how you write either the bottom or the top, because these two are exactly opposites of one another. You can rewrite the top by factoring out or dividing out a -1. If you factor out a -1, then you can rewrite this as -1 times -x plus 4, or 4 minus x. All right, we have a factor that divided out. There is going to be a hole at wherever 4 minus x equals 0. Pretty sure it's 4 minus 4 equals 0, so it's x equals 4. Now what's the y value? Well, that depends. What's the new function we've got? It's -1 divided by 4 plus x. I'm just going to call it x plus 4. Okay, that's interesting, because there's a domain issue that did not divide out. If I plug in 4, I get -1/8. So here's the deal. Yes, we can plot the hole at 1, 2, 3, 4 down 1/8. Right, so that's where we're going to have an open circle. Hopefully you guys can see that. Get a little closer. Yep, it's not a closed circle. It's an open. Sorry, you guys weren't ready for that. I'll warn you next time. So now, you're graphing that as is, as if it were something from yesterday's assignment. So now what you should be thinking is, hey, I have a vertical asymptote at -4. So you'd go left 4 and draw a dashed line vertically. Horizontal asymptote? Ha! The bottom power is bigger than the top power, or at least the leading one. Y equals 0. Which means we're probably going to level out at 0 on both sides of the vertical asymptote. Is there a 0? No, the top equals 0, that's gibberish. Doesn't cross the x-axis. So now we plot a few points. You can go to your table in your calculator, 1, 2, 3, 4. I'm just going to plot -3. -3 would give me -1. -2 would give me -1/2. -1 would give me -1/3. 0 would give me -1/4. 1 would give me -1/5, and so on and so forth. If I did -3.5, I'm going to get -2, and then it gets infinitely closer to the x-axis as you keep moving downward. And then you could probably expect that this is going to be where the other part of the curve is. Don't assume, though. Make sure you check some points. So if you plug in -5, you're going to get +1. Let's get this guy out of here. Well, you remember what I was plugging into, right? -6 would be 1/2. -7 would be 1/3. And it just follows that same pattern again. Halfway between here and here is going to be halfway between there and there, up 2. All right, so you've got an asymptotic function that still has a hole over here. All right, I hope you guys found this helpful, and it's making sense. Thanks for watching.